Bit manipulations is a secret weapon that an experienced developer will always have. It is true that you will not be asked questions directly on bit manipulations in an interview. But this is something which can separate you from all of the other candidates and give you a kind of a competitive edge. This particular problem will give you a perfect example about it. Hello friends, welcome back to my channel. And we are working on our mini series on bit manipulations. In this particular problem, we will be taking the help of two concepts that we have previously discussed. Particularly, I'm talking about truth tables and determining how you can check if a particular bit is set when you're given a particular number. So if you're unaware about these concepts, I would highly recommend you to stop this video right over here and check out my previous videos first. If all of these terms sound pretty familiar to you, you are ready and let's get started. In this particular video, we will be discussing about the concept of a power set. So how does a typical problem look like? When I talk about a power set, it simply means all the total different number of subsets possible when you are given a certain number n. So for example, when the value of n is 0, when you have no numbers available, then how many subsets can you form? There is only one type of subset possible which doesn't have any element. So this is the subset available to you and there is only one subset that you can make, correct? Now when you go ahead, let us say the value of n is 1. It means that you are given a starting condition where you have a set and only one number is present, and that is 1. So how many sets can you make? How many subsets can you make? You can choose not to pick up any number, or you can choose to pick up the number that you have. That's it. You cannot have any other combination. So you got a total of 2 subsets, correct? And this is the power set. Similarly, when the value of n is 2, what happens now? You now have 2 different numbers possible, 1 and 2. So how many different type of subsets you can make? Either you can choose not to pick up any element, you can either choose to pick up only the element 2 or the element 1, or you can pick up both the elements 1 and 2. So this is your complete power set. And how many subsets you could make? You could make a total of 4 subsets. So actually there are 2 things in this problem. This is the total number of subsets that you can make, and this is the complete power set. And we will be utilizing both of these concepts. What happens when the value of n equals to 3? It means now I have 3 elements possible. So you can see that the number of combinations, they are gonna increase drastically. And these are all the possible combinations. You can either choose selective numbers, or you can choose combination of numbers, or you can choose all the 3 numbers. That's it. You have now exhausted all of your possibilities. This is your complete power set, and you could see that you were able to form a total of 8 different subsets. So once again, we have both the information available over here. That's the first part. At least you now understand the problem. Now, where do you begin? If you want to think about the brute force approach, sure, you can start off with every possible combination and try to form all of these different methods, correct? Or you could also try the recursive approach and then come up with a solution. But what about a bitwise approach? How you can take advantage of it? Well, before going over there, we need to understand what is happening with the value of n and the total number of sets possible. If you might have already observed, when I look at the powers of 2, if I don't have any element, then what does it mean? It means 2 to the power of 0, and it simply means that I will have only one set possible. That is the only subset. What if I have one element? That means 2 to the power of 1, and that equals 2. It means I can have 2 subsets possible. When I have 2 elements, 2 to the power of 2, and that means I will have 4 subsets possible. Similarly, for 3 elements, I will have 2 to the power of 3, and that means I can have 8 different subsets. As this value goes on to increase, when you have 4 elements, then it will be 2 to the power of 4, and it means you are gonna have 16 different subsets. So at least we know one piece of information. If I know the value of n, I can determine that, okay, these will be the total number of subsets possible. This is not just a trivial piece of information. You have actually determined what are the total number of subsets possible. And you can also find that out using the bitwise operators. If you do 1 left shift of n, that will give you all of these corresponding values. If the value of n is equal to 3, then what happens once you do one left shift of 3? It means 1 followed by 3 zeros. This, when converted to decimal, gives you 8. So, instead of raising the number to the power of 2, what you can do is you can simply do a left shift by this n, and it will tell you whatever are the total number of subsets possible. So you can think like, okay, I need to return some kind of a giant list that will have all of these subsets in them, correct? If I am talking about a power set, think about it. If I have 3 elements, I know that I will have 8 elements in my power set. And all of these 8 elements will be lists in itself. So I now know a crucial piece of information, that I need to make a final list that will have these number of elements, correct? Now we have sorted this out, we can focus on the other aspect of the problem, that is finding out all of the different possible combinations. And that is where the concept of a truth table comes back again. If you remember, what was a truth table? A truth table determines all the different possible combinations that can happen when you are given a certain number of bits. For example, I have 3 bits over here, and these are all the possible combinations. I cannot have any other combination other than this. And if you count all of them, these are a total of 8 combinations. So it kind of aligns with what we were thinking, right? We wanted a total of 8 different subsets, and these are all the 8 different values. We just need to utilize them somehow. If you also notice that these are all the decimal values. So I'm going from 0 all the way up till 7. And what is 7? Total number of subsets minus 1. So it might help to write a for loop of some kind. But we will get to it later. For now, try to think, how can we generate all of those combinations? Once again, I have my array over here. And I have all of the 3 elements available, correct? Now, what I can try to do is, I can try to map these 3 bits onto all of the 3 given elements. Perfect. Now, let us try to look at each of these rows with respect to what bits are set or not. If you look at this first row, it is telling me that none of the bit is set. It means that I do not need to take any of these elements. So, is it safe to say that I can find out the first subset by not picking any element, correct? Now, go on to the second row. In my second row, I say that, okay, only pick the element at A. Do not pick the element B and C. Can I use this to find out my second subset? What did I say? Only pick the element at A. So I am picking only this particular element. It is giving me a subset. Let us try to continue this approach and see what happens. I need to find out my next subset now. Look at the next row. I am saying do not pick up C, pick up B, and do not pick up A. So I'm only picking the element B. Once I pick this up, I can write down a 2 over here. That means I got another subset. Let us look at the next row now. In my next row, I am saying do not set C, but set B and set A. So I'm gonna set both of these. So I get 2 and I get a 3. Similarly, in my next row, I set the element C, so I get a 1 over here, and both the other elements are 0, so I do not set them. In the next row, C is set and A is set. So I can create one more subset, 1 and 3. Similarly, if you do it for 2 more times, in this next row, I get C and B as set, so I get 1 and 2. And in the last row, all of the bits are set, so I pick up 1, 2, and 3. That's it. There are no other combinations possible. And what is this giving you? It is giving me my complete power set. And this is true because these are all the different possible combinations that we can have with 3 available bits. That means I cannot have any more combinations possible, and I have exhausted all of my possible combinations. So this makes things super simple, right? So if someone asks you that how are you sure that this method will work? Well, you can say that because my truth table covers all of the possibilities, I know for a fact that these will be all the possible subsets, and this is my power set. So this is all of the theoretical concept. But if you have to write a code for this, how do you do it? How do you check that was this bit set or not? Up till this example, we were able to see with the naked eye, correct? But how do you do it programmatically? That is where we will be leveraging the concept that we previously discussed. Given a number, how do you determine if a particular bit is set or not? That means if I give you the number, let's say 83, and you have to tell me, hey, is the fourth bit set or not? This is the concept that we will be using. So if you're unaware about it, stop right over here and check out my previous video first. Because only when you learn that, you will be able to understand the code that we're gonna write. Assuming that you're familiar with all of those concepts, let us try to understand how we can write the code for this. What is the first thing that we do? First of all, we need to determine what will be the total number of subsets possible. So given this value of n equals to 3, I know that this will be my starting set. And how many total subsets are possible? I do one left shift of n. So this is gonna give me one left shift of 3, and that gives me the number 1000. This is equivalent to the number 8. So the value of total subsets, this is gonna be set to 8. Correct? Now comes the next part. I am initializing my power set. This will be the final answer that is gonna have all of the subsets. And how many subsets do you have to make? You have to make a total of 8 subsets, correct? So given the programming terms, what I can do is I can start from 0 and loop until total subsets minus 1. That means 0 up to the way to 7. I know that I will have 8 subsets, and in this loop, after each iteration, I should be able to insert one of these subsets in my power set, correct? This is the idea over here. And this is the scope of this particular loop. As soon as this loop starts, what do I do? First of all, I will start a subset. What does this mean? It simply means that I am gonna create an empty set. This particular subset should now be filled up, and once it is ready, we add it to our power set. This is the approach we're gonna follow. So now is the time that we try to fill up this entire subset. And how can you do it? If you now try to remember, what did we do in our approach? For every subset, we were checking if this bit is set, then I need to pick up the number, otherwise not. If this bit is set, then I need to pick it, otherwise not. So what were you doing? You were doing this for each of the 3 bits, correct? Check out once again. What were you doing? For each of these subsets, you were checking each of these 3 bits. If a particular bit was set, then you set the value, otherwise you left them out, correct? So we are gonna follow the same approach over here. I am gonna start a for loop, and this loop will check each of the bits for every subset. And how many bits do I have? I have a total of 3 bits. So I will start my loop from 0 and I go all the way up to n minus 1. That means 0, 1 and 2. I check the 0th bit, I check the first bit, and I check the second bit. And if any of these bits are set, I need to pick up that value, correct? And that is exactly where I will revise one of my previous concepts. I need to check if the ith bit is set or not. So what are we doing? We are looping this value num from 0 all the way up till total subsets minus 1. So I'm gonna go 0, 1, 2, 3, 4, 5, 6, 7. And for each of these numbers, they represent a row in my truth table. And for each of these numbers, I am checking if the 0th bit set, if the first bit set, if the second bit set. What do I do if this particular bit is set? I just say subsets.add and I pick the number from the array. So I is telling me the bit to pick. So I am saying ARR at I. So if the 0th bit is set, it is going to pick up this number. If the first bit is set, it is going to pick up this number. If the second bit is set, it is going to pick up this number. So based upon the fact that if a bit was set, this value is going to pop up in my subset over here. So let us say, for example, the 0th bit was set and the second bit was set. So in my subset, I am going to have the value 1 and I am going to have the value 3. This loop will be very, very small, right? Since I only have 3 bits to check. Once this is done, I know that my subset is ready. And once I know this, what do? I say power set.add subset. So what is going to happen is this entire subset, it goes in your power set. What will happen in the next iteration? Once again, you will start off with another number. It could be number 6. And now, once again, you start off with an empty subset. You check all of the 3 bits again. Whatever bits are set, it could be 2, 3. Now your subset is complete and you add it to your power set. So I know that once this entire loop is completed, I have exhausted all of the subsets that I can have. Once that is done, I simply return my power set and this will be my answer. Pretty simple, right? You did not have to do any combinations, any recursions. Just by the power of bit magic, you were able to solve this problem so very efficiently. And this in fact works very, very fast. You know that there will be 2 to the power of n combinations. So naturally, that has to be your time complexity. Order of 2 to the power n, because that is the maximum number of times your loop will run. And you're also checking every bit in every iteration. Now, even if you're given the largest number, that is 2 to the power of 32, you still have only 31 bits to check. That is not a huge number, and you can say that this particular operation is gonna happen in constant time. So the overall time complexity of your solution just turns out to be order of 2 to the power n. And similarly, the space complexity will also be order of 2 to the power n, because you need to return this complete power set. You are going to take up the entire space for storing all of these numbers and then returning them. I hope this now makes a lot of sense, and you might be able to see how we use the applications of all of the bit magic techniques. And that is why I had been emphasizing for so long that make your fundamentals very, very strong. Because if you are unaware about how do you clear a bit or how do you even check a bit, then you will never be able to even land at this solution. Even if you figure out the truth table, you can never reach a solution where you are determining that, okay, I need to check if this bit is set or not. And how can you make it happen instantaneously? How can you do it in a constant time? That is where the efficiency lies. And you can easily see that if you are going to use this particular code, it is going to be very, very fast than any kind of recursion or any kind of combinational technique. Do let me know in the comment section below, what did you think about this? Can you find any other efficient method by which you can find all of the different combinations when you are given a particular array? And notice that the ordering of these particular subsets does not matter. You can return them in any order. I'm going to do a couple more of these videos to show you the applications of all of these bit manipulations technique. So make sure you're subscribed. And as per all of my members, I want to give you a huge shout out. You guys are the real rock stars, and it really keeps me motivated to see all of you. And obviously, as a member, you do get priority reply to your comments and early access to new videos as well. And also remember that now you can schedule a one-to-one session with me and we can discuss about almost anything. Stay tuned for my upcoming video. Until then, see ya.